Today we're going to be discussing audio interface settings. We're going to talk about sample rate and bit depth, as well as buffer size and latency and how those two things correlate. Hello everyone, and welcome to WaveSpot. My name is Austin Knaus, and I've spent the last 2 decades working with audio. My goal for this channel is to share all the fundamentals that I've learned along the way and hopes to give you a fast track to understanding the world of sound. So, let's dive in. There are 4 primary settings, really 3, with a 4th being a result of one of them, that will affect your audio quality and your ability to record in real time. And those 4 things are sample rate, bit depth, buffer size, and latency. So the first one that we're going to talk about is sample rate. So what is sample rate? Sample rate refers to the number of times per second an analog audio signal is measured and then converted into a digital signal. Sample rate is measured in hertz, or primarily kilohertz, kHz. Sample rate, in simple terms, is how many times per second your interface looks at the audio and takes a picture. We can think of a sample as like a picture, and we can think about how a movie is a bunch of moving pictures. So essentially, sample rate is how many pictures per second are being taken. The higher the sample rate is, the more pictures are being taken per second. So why do we need to sample? Well, there's 2 different kinds of audio that we're going to be working with, analog and digital. For example, the human voice, the wind, a guitar, the drums. These are all analog signals. We have microphones that capture analog signals, and then it transfers that analog signal to an audio interface. That audio interface then goes and turns that analog signal into a binary signal, the ones and zeros like you see in the Matrix, the ones that computers can understand. The computer can only understand binary, ones and zeros, whereas an analog signal has an infinite amount of variation. So where the computer can only understand a 1 or a 0, an analog signal has a decimal point. So it can go down to 0.00000000000 all the way up to 1. And this process that's undergoing analog to digital is called analog to digital conversion, or ADC. For an example and an oversimplification to understand the concept, check out this picture. If we had a sample rate of 5, this means that we have 5 samples per second. This picture would be the same signal, but at a sample rate of 22. This would be a sample rate of 44. This would be a sample rate of 88. So you can see that the higher the sample rate, the more pictures or samples we're able to take of the same audio signal. Lucky for us, sample rate is primarily measured in kilohertz, or thousands of times per second. In fact, the minimum base sample rate is actually 44.1 kilohertz, or 44,100 times per second. And what the audio interface does is converts those samples into binary bits of information that the computer can understand. Here's a couple of different sample rates. First, we have 44.1K, which is standard for CDs and most digital audio. 48K, which is common in film and high-end fidelity. 96K is primarily used in professional audio recording. And 192 is ultra high fidelity and used in specialized applications. Normally we record in 96K. That makes it all the way through to mastering, and then it gets downsampled into 48 or 44.1 for CDs and digital distribution. But if your computer can't handle running at 96K, 48's fine and 44.1 is just fine. You can't record something at 44.1 and then later on, after you're done, upsample it to 96K. It doesn't work like that. You can always go from 96 down to 48 and then down to 44.1, but you can't go from 44.1 to 48 or up to 96. You can't expect to save a file and then get more quality out of it later. it is what it is. Once it's saved, it's saved. So this leads us into bit depth. So what is bit depth? If sample rate is a picture, then bit depth is the quality of the camera. For example, if we took a picture with an early 2000s flip phone, we would get the picture, but there wouldn't be much detail to it. If we compared that to whatever iPhone or Android is on the market today, we would have impeccable quality, depth, and richness of color when compared to that early 2000s flip phone. While sample rate is how many pictures are taken per second, bit depth is the quality of those pictures being taken. Let's use another oversimplification, and let's go back to our sample rate of 5. But this time we're going to add a bit depth of 4. So this means there are 4 bits per sample. If we look at this picture, we can see that each pink dot represents a bit. And if we connect all the dots in our signal, it would look something like this. And you can see where there should have been a curve in the wave up at the top. There's now kind of a blocky, choppy representation of what that wave was. The signal gets translated, but kind of poorly. So what if we doubled the bit depth but kept the same sample rate? You can now see that we have 8 bits per sample instead of just 4. And if we remove the audio signal from behind it, you can see that it's a lot smoother than the previous bit depth of 4, even though we still have the same sample rate. So those are small numbers. Our bit depth is measured in 16, 24, and 32 bits. You can think of bit depth as the resolution of the picture or sample. A picture or a sample that is made up of 16 bits is going to have less resolution than a picture or a sample that is made up of 32 bits. If we're running at a sample rate of 48K and a bit depth of 16, this means that there are 16 bits for every single one of those 48,000 samples. If we up that to 32, we essentially double the amount of information per single sample taken. Not only does it increase the resolution of your audio, it also drastically increases the size of the file.
Big settings equal big storage space.
Another example for bit depth. Take a look at Mario. 8-bit Mario has 1 skin tone. 16-bit Mario has about 2 to 3 skin tones. 32-bit Mario now has shades because the bits are so fine that we can't really see them, but they still aren't fine enough to give enough detail to create fingers. 64-bit Mario now has fingers and even visible definition in his ears. You can have 44,100 16-bit Marios, or you can have 48,000 32-bit Marios. I hope that gave you a good visual representation on how bit depth can affect the quality of your audio. And just like sample rate, the higher the bit depth, the more CPU processing power we're going to require from our computer. The common bit depth standards that we're going to be working with are 16-bit, which is standard for CDs and consumer audio formats, 24-bit, which is common in professional audio recording and production, and 32-bit floating point, or 32-bit float, is used in high-end production setups. So now you can see that sample rate and bit depth directly affect the quality of your audio. Now let's get into buffer size. What is buffer size? Buffer size is essentially how many samples you allow your computer to process before it comes back out of your speakers. You can think of buffer size as a bucket that will dump its contents every time it gets full. And for example, let's say there's 2 buckets. Our first bucket is small. It can only hold 64 samples. Our second bucket is pretty big. It can hold 1,024 samples. The buffer that can only hold 64 samples will dump its contents 16 times before the second buffer will dump its contents once. This means that your computer is working 16 times faster when you're using a buffer size of 64 as compared to a buffer size of 1024. When processing audio with a computer, the computer needs a little bit of time to actually process the data you're giving it. Buffer size doesn't just determine how many samples are processed before playback. It actually determines how much time your computer has to process that information. The larger the buffer size, the more time your computer has to process, but this introduces latency. You can think of latency as how long it takes for our buffer bucket to fill up. Smaller buffer sizes process fewer samples and reduces latency, but it increases the strain on your computer. Sometimes it can even cause pops and clicks if the computer can't keep up. Other times, it can get so bad that it just freezes your computer or crashes the DAW entirely. This is because you're not giving your computer enough time to process the information. So, what exactly is latency? Latency is the amount of time it takes for your voice to enter the microphone, to travel to the interface, be processed by your DAW, back to the interface and out of your speakers or into your headphones. It's also known as round-trip latency. Latency is measured in milliseconds, and if it's long enough, it can produce an audible delay between the time you speak and the time you hear it back in your headphones. This occurs simply because it takes time for your computer to process the information. With the buffer bucket example, the buffer bucket that can hold 1024 samples takes 16 times longer to fill up than the buffer bucket that can hold 64 samples. The time difference there is latency. Smaller buffer sizes result in shorter latency times. This is crucial for live performance and live recording. Larger buffer sizes allow more time for your computer to process the information, but this induces more latency. These can be good for larger projects and mixing and mastering, but it's not a good idea for live performance and recording. So here's a couple of different buffer sizes and their equivalent latencies. 64 samples is a very low latency at around 1.45 milliseconds, but it does require quite a powerful computer. 128 samples is low latency at 2.9 milliseconds and is suitable for recording and monitoring. 256 samples is a moderate latency at around 5.8 milliseconds and is ideal for balancing and recording as well as processing. 512 samples is getting into high latency at 11.61 milliseconds. This is better for mixing and mastering when latency is less critical. 1024 samples or higher is considered very high latency. This is around 23 milliseconds, is considered unusable for live performance or recording processes. I personally have gone up to a buffer size of 2048 samples in some extreme situations. It all depends on what you're trying to do and what your computer can handle. If you're trying to do live recording, a smaller buffer size is preferable because of shorter latency times. If you're only mixing and mastering, you can use a higher buffer size without really noticing a difference. So in summary, sample rate is how many times per second our audio interface takes a picture or a sample of our audio. Sample rate is measured in kilohertz, and the base minimum standard for audio production and as well as CD quality is 44.1 kHz. Bit depth refers to the quality of those samples being taken. The more bits of information you have per sample, the higher the quality your audio will be. Standard CD quality is 16-bit, with high fidelity projects being 32-bit floating point. Buffer size is how many samples you are allowing your computer to process before forcing it to play it back through your speakers. The smaller the buffer size, the fewer the samples your computer has to process before playback. This is also very CPU intensive and requires a lot of computing power. The larger the buffer size, the more samples and more time your computer has to process the information, but it increases the amount of latency you have. Latency refers to how long it takes for your buffer to process. Latency, or round-trip latency, is referring to how long it takes for the audio to enter the microphone, into the interface, processed by your DAW, back to the interface, and out to your headphones or speakers. Latency and buffer size are proportionate to one another. The smaller the buffer size, the smaller the amount of latency. The larger the buffer size, the larger the amount of latency. Your computer's processing power and buffer size are inversely proportionate, meaning the smaller the buffer size, the more power is required to process. The larger the buffer size, the less power is required to process, simply because we're allowing our computer to use more time to process things. Sample rate and bit depth directly influence the quality of your audio, while buffer size indicates the amount of samples your computer processes before playing it back to you. Latency is the measurement of time it takes for your computer to buffer the samples. If you found any of this information valuable, be sure to hit that subscribe button. I release a new video every Monday morning. If you learned something new, or if you still have questions, leave a comment below and I'll be sure to get back to you. If you want to read more on the topic, head over to wavespot.com, where I have more detailed information as well as all the illustrations from today's episode written in a blog post. And until next time, thanks for watching.